The next topic is thermal stress. As usual, let's have an introduction. So before we go into thermal stress, whenever there's stress, there's strain. Therefore, we have thermal strain. And its symbol is epsilon sub T. Symbol of strain is epsilon. So to specify that it's thermal strain, we have a sub T. And it's the strain caused by changes in temperature. The equation is epsilon sub T equals alpha change in T, where alpha is the coefficient of thermal expansion, and change in T is the change in temperature. So final temperature minus initial temperature. And remember, okay, the equation for strain is deformation over original length. Am I right here? But anyway, it's deformation over original length, right? So equation for strain, alpha change in T. Now that's also equal to delta over original length L. Multiply both sides by L to get alpha L change in T. So this is a deformation due to temperature. And again, when there's strain, there's stress, and vice versa. Thermal stress is the stress caused by internal forces when the deformation of a body is restricted. So later on, you'll see in the examples what we mean by restricted. Okay, so just keep that in mind for now. Now, this is the procedure in solving for thermal stress and strain. First step is relaxing the supports. So remove the constraints that prevent the thermal deformation to occur freely. Next step is draw a sketch that exaggerated the magnitude of deformations and derive compatibility equations. Next, apply the forces that are necessary to restore the specified conditions of constraint. Add the deformations caused by these forces to the sketch that was drawn previously. And then write the relationship between the thermal deformation and deformation due to constraint forces. So basically, remove constraint, okay, allow your object to deform. Once it deforms, apply an external load to make it go back to its original position. And then we already know the deformation due to applied loads, right? So we're gonna compare that to the deformation due to temperature. So that's basically the method of use. First, to better understand, let's have a few examples. Number one, a steel rod with a cross-sectional area of 0.25 inch squared is stretched between two fixed points. The tensile load of 70 degrees Fahrenheit is 1,200 pounds. What will be the stress at 0 degrees Fahrenheit? At what temperature will the stress be 0? Assume alpha equals 6.5 times 10 raised to negative 6 inch per inch degree Fahrenheit, or simply per degree Fahrenheit. And then E is 29 times 10 raised to 6 psi. So let's understand the problem. You have a rod, it's stretched out to a certain point. And then the first question is, what will be the stress if we change the temperature to 0 degrees? So let's focus on that first. Okay? So number one, let's write out our given first. So you have the cross-sectional area of a rod, which was 0.25 inch squared. Next, we have your initial temperature, right? So this is your initial temp, 70 degrees Fahrenheit. So Pi. And then the load at your initial temperature is 1,200 200 pounds. Then for part A, the final temperature is 0 degrees Fahrenheit. Okay. Another thing that's given is your coefficient of thermal expansion, 6.5 times 10 raised to 6 negative 6 per degree Fahrenheit. You can just write it as that, or inch per inch degree Fahrenheit. Then E is 20. Now take note, our unit for E, PSI, so therefore standard unit is pounds and inches. Okay, so let's begin. So I'm gonna explain or solve number 1 on my own. You just have to listen. Okay. So let's draw the original position of your rod without it being stretched out. So let's assume it's only being stretched out in one direction. So it's gonna be fixed on this end. Okay, so let's say this is our rod. Okay, that's the original length. And then eventually, this is stretched out to a certain point here. Okay. So that stretching is a physical applied load. Therefore, this is a deformation due to load. Okay. Make this more colorful. Great. Original length. And then, so this once again is our deformation due to load. Okay. Now, after it's being stretched, okay, we have our final temperature as 0. So initial is 70, final is 0. So it's getting colder. And based on your physics classes before or based on observation, we know that as temperature gets colder, our objects contract. So what happens here is it goes back to a certain point. Okay? So the temperature that will apply will be on the original block. Okay? Because whether it's stretched or whether it's just like this, the amount that it deforms due to temperature is the same. So just to make things clearer, will depend on the original length. Okay? So again, this is your original length. Due to freezing or due to decreasing temperature, it goes to this portion. Okay? So this is again how much it deforms due to temperature. So let's label that your delta sub T for deformation due to temperature. Now, from here, you'll see, remember in the step, right? This is how we'll do it. Okay. So the initial position was this. The problem states that it was stretched. Okay. And then we're going to relax the supports. Okay. So when you relax the support, your object or your rod will go back to this position. And then decrease in temperature is going to shrink further. Okay. And then the next step after letting it deform, apply the forces necessary to restore the specified conditions of restraint. So now we're gonna apply another force to make it go back to its original position, meaning we're gonna stretch it out to this position again. Okay? Because this is the original position of your rod. Okay, when we relax the support, it turns into this, and then decrease temperature, it turns into this. Then apply force, right, to make it go back here again. Okay. So this is it. Then this is now its deformation afterwards. Right. So wait. Okay. So looking at this drawing, okay, so this is the total deformation, okay? Let's call it sigma. Then let's call this sigma P for deformation due to force, deformation due to temperature, deformation to apply another force to make it go back to its original position. Now from this, we can create an equation relating all of our deformations. And as you can see, total deformation is just deformation due to temperature plus deformation due to force. So once again, drawing is important because this is where we'll base our equation. So total deformation, temperature plus force. Okay. And then let's go back to what we're looking for in the problem. Stress at 0 degrees. So I'm going to use the equations for stress for this total deformation. Okay. So sigma L over E. Now this is what we're looking for, right? Total stress in the system. Deformation due to temperature is alpha L, change in P, right? And then deformation due to an existing load is this. And look at what's given. We're given the applied load. So instead of using sigma L over E, we're going to use PL over E. Okay, sub in our values, sigma, again, this is what we're looking for. L is original length of your member. Original length. Same thing here. L is also original length. Same thing here. L is also original length. So even though we didn't have a given original length, we didn't need it because, as you can see, everything cancels out. Okay, then over E. E is given 29 times 10 raised to 6. That equals alpha. Alpha is 6.5 times 10 raised to negative 6 per degrees Fahrenheit. So make sure your change in temperature is also per degrees Fahrenheit. Final temp is 0. Initial temp is 70. And then plus P over AE. Again, P, pounds, PSI, so uniform units. No need to convert. 1,200 over A. It's in inches, so no need to convert. And then E, again, it's 29 times 10 raised to 6. And then from this, as you can see, we can solve for stress. And stress is just 17995, 17,995 PSI, since our units are pounds and inches. Okay, so this is part A. Next, what about part B? Part B, at what temperature will the stress be 0? Assume. So now our stress is 0. So in what situation is stress 0? That's when all the deformations cancel out, right? So for example, in this scenario, the reason why this is experiencing stress is because you stretched it out and then it made it deform. And then you're stretching it out again. Okay? So to make it not experience stress, we need to create a situation where you don't need another applied force. So that means, okay, we need to create a temperature wherein its expansion will lead it to the same point as the original applied force. Okay, so in drawing, Again, so once again, this is a deformation due to the original applied force, right? For it to not experience stress, the deformation should, due to temperature, should be equal to that. Yes. Okay. Stress. Temperature. So this is deformation due to applied load, and then deformation due to temperature. Okay? Can you imagine, for example, if the temperature is enough for this end to go to this end, right? Therefore, the force applied here would be null because it already extended up to that. This only extends this so that it reaches this point. Okay? That's how it experiences zero stress. And then from the drawing, you create your equation again. So the equation is deformation due to temperature will be equal to deformation due to force. Okay, sub in values, alpha L change in T equals PL over AE. Again, L cancels out. Alpha is 6.5 times 10 raised to negative 6. And then change in T is your final temperature, and that is what we're looking for, minus your original temperature, which is 70, equals P. Again, P is 1,200 over AE. And then from this, we can solve for TF. TF is 95.46 degrees Fahrenheit. So we need to heat up the system to 95 degrees so that the system doesn't experience stress anymore. Okay? That's number one. Any questions for number one? Please answer in the chat. Okay, no questions. Let's move on to number two, and I'll be taking recitation. Number two, steel railroad reels 10 meters long are laid with a clearance of 3 millimeters at a temperature of 15 degrees Celsius. At what temperature will the rails just touch? What stress would be induced in the rails at that temperature if there were no initial clearance? So show alpha 11.7 micrometer per meter degree Celsius and E equals 200 GPa. So basically, you have a system of railroad rails and a spacing. Then, first of all, we're looking for the temperature so that that gap closes, meaning your rails touch. Okay, so that's our first goal. So let's write out our given first. Initial temp 15. What else? Original length is 10 meters. And then alpha 11.7. Now take note here. It's micrometer per meter. Okay? So we need to cancel that. We need to have uniform units. So recall 1 micrometer equals 1 times 10 raised to negative 6 meters. Okay, so I'm going to introduce this conversion unit, the conversion value, so times 10 raised to negative 6, so that they're both in meters. So meter per meter degree Celsius. So now this is just per degree Celsius. All right? So take note of your units. And then E is 200. So let's draw this. Okay, let's have railroad rails. Let's have this, right? Okay. So these are our rails. And then this is 3 millimeters apart. Same thing here. That's our clearance. So again, the question is, at what temperature will they touch? So we need this to expand. So there's an increase in temperature, and then the final position would be this, right? They're touching here. So first, let's figure out how was it extending. Okay. So since there's no restraint on any side, okay, the rails will expand in both directions. Okay, so meaning this is how much this piece of rail expands on this side, and this is also how much this piece of rail expands on that side. Okay, so therefore, total deformation is divided from two sides. So we're gonna write here deformation due to temperature over 2, and then deformation due to temperature over 2. And then total deformation, therefore, we can say is this part over 2, that's 1.5, right? This is also 1.5. So 1.5 times 2. So total deformation still comes out to 3 millimeters, right? Okay. Again, total deformation adding from the left to the right is still 3 millimeters because this is 1.5 and this is also 1.5. Okay, so total is 3. And then from this, we can create our equation. So the equation here is alpha L change in T equals 3. Okay, alpha is 11.7 times 10 raised to negative 6. Length is 10 meters. Our units are in Newton millimeter. So 10 times 1,000. Okay. And then change in T. TF is what we're looking for. So TF minus initial temp 15 equals 3. From this, please solve what's TF. Correct, Krishaline and John. Paragua and Frias. 40.64 degrees Celsius. Okay, so that's our first answer for part A. How about for part B? What stress would be induced in the rails at that temperature if there are no initial clearance. So now, since it's going to be restrained, there's no clearance, there's no room for the rails to expand, it's going to experience stress. And let's draw that. Okay. So remember, so let's consider just a single rail. So remember, when your rail or when your object is restricted, okay, the first thing you do is to remove that restriction. Okay, so let's remove that. And again, once we remove it, it's gonna expand this way by an equal amount. Okay, so again, the expansion is equal, and this is expansion due to an increase in temperature to this. So again, equally distributed on each side. So this is delta T over 2, delta T over 2. And then the next step is to apply loads so that this goes back to its original position. So from this position, right, it's gonna go back to this. This is due to applied loads at each end. Okay, so this is now how much it deformed due to an applied load. So sigma P over 2. Sigma P over 2. Okay? So from this drawing, we can create our equation. And as you can see, the amount it expanded in total is also equal to the amount it contracted due to the applied force. So in short, delta T is equal to delta P. Okay? So what are we looking for? Stress, right? What stress? So we'll use the equation involving stress. So sigma L over E for temperature. So for temperature, its constant is alpha A, alpha L change in T. And this is your sigma L over E. Okay. Again, original length is the same. So that cancels out. Alpha is 11.7 times 10 raised to negative 6. Change in temperature is your TF, which is what we solved. So store that. 40.64. Initial temp is 15. And it's equal to stress over E, which is 290, 200 GPa. Convert to MPa times 10 raised to 3. Okay, so from this, please solve what is stress. Correct. $60. So if you use the stored values, you'll get a whole number 60. So correct, DMA and Colleen. So Vergara and 60 NPA. Okay, and that is our answer. Part 2. Okay, so that's number 2. Any questions for number 2? Please answer in the chat. Okay, good. Let's move on to number 3. Number 3. Calculate the increase in stress for each segment of the compound bar shown in the figure. If the temperature increases by 100 degrees Fahrenheit, assume that the supports are unyielding and that the bar is suitably braced against buckling. So basically, there's an increase in temperature and we're looking for the stress it created. Okay, so first step is your equilibrium equations. So previously, we didn't need any because there's no applied force here. There's no reactions as well. However, here, that's a different story. Remember, we've had these kinds of systems before. And we know, I'll move this here. We know that whenever we have something like that, there's actually reactions at these points. So R1, either this is R1 or 2. Now, if we do summation of forces equals 0, there's no applied force here. You'll see that R1 minus R2 equals 0. So R1 equals R2. There. Okay? So that's our first step. Next, to get the stress in each segment, we need to get the internal force it's experiencing in each segment, right? And to get the internal force, you can cut isolate. So cut isolating, you have R1 here. And then let's call this PAL. Okay? And then again, summation of forces equals 0. You'll see that PAL is equal to R1. I'll do the same thing for the other side. Okay, so next here, smaller. So again, there's R1, R2 over here. And then there's PST for steel. And again, if you do summation of forces equals 0, PST equals R2. However, R1 is equal to R2. So therefore, PAL is just equal to PST. And you can just call it P. Okay? Now the goal is to search for P and then divide it by the area to get your stress. So now how do we do that? Again, we're going to go through our procedure. First step, relax your supports. Okay? Just get this. So relaxing your supports and let your system expand or deform wherever it should. Okay? So if you relax your support, obviously, this will extend here, right? Due to an increase in temperature, creates expansion. Okay? So that's why these two ends will expand. Okay, so let's do that. So this is how much it expands due to temperature. Same thing here. But this is for aluminum, this is for steel. Next step is to apply force so that doesn't, or it goes back to its original shape. Okay. And again, there's an applied force here. Put it back. And then this is how much it deforms afterwards when you put it back. So sigma delta P, same thing here, delta P. And then from the drawing, again, you can create your equation. So if you've noticed, the total deformation due to temperature is this, although from different materials. That total deformation is still equal to the deformation due to your force. Okay? So therefore, delta T again is equal to delta P. Here, this is the total deformation of aluminum and steel. So summation. Okay, so let's start first with aluminum. Same equation, sigma L change in T, again of aluminum, plus alpha L change in T for steel equals, we're looking for force, so we'll use PL over A. So PL over AE of aluminum plus PL over AE of steel. Okay. Now we can't remove L because they're all different lengths, right? This is not equal. So we cannot cancel that. So now let's just sub in our values. Alpha for aluminum, 12.8 times 10 raised to negative 6. Original length, 10 inches. Okay, so 10. And then change in temperature. Let's check again here. Temperature increases by 100. So there's a positive change in P. So let's include that here. So this is 100. Positive since it's an increase. Then plus alpha of steel is 6.5. Original length is 15 inches, so 15. And then again, change in temperature is the same, positive 100. Then equate that to PL over AE. This is PAL. I'm gonna move this down. Okay. So PAL, PAL aluminum. Original length again of aluminum is 10. Area of aluminum is 2, and then 10 times 10 raised to 6. Okay? And then plus PST, original length 15. Area is 1.5, and then 29 times 10 raised to 6. Okay, now we already know PAL equals PA, PST. Therefore, this is just P. Okay, and from this, please solve what's P. Correct, Micaela? Wala pang yun. Okay. Correct, Edwin. Yeah. So it's 26,691.84 pounds. Now we're not done. Again, we're looking for stress in each segment. So to get stress in AL, this is P over area AL. And area AL is 2. So what's the answer here? What's stress in aluminum? It's divided by 2. Again, aluminum. Correct. Nina and Miguel. Flores Moon. It's 13,345.92 psi. And then stress in steel is just P over area of steel. So divided by 1.5, what's the answer? Correct, Aaron. And correct, Micaela, but 2 points ka na. So Julie, Solomon, and then 17,794.56 PS. Okay, and that's how you solve. So that is number 3. Now, for example, if there's an applied force here, P, okay, that's just gonna apply here, right? Actually, here, we're gonna have a relationship between R1, R2, and that force P. That's gonna be our equation 1. And then you're gonna have these equations. And then from that, we can create a relationship between PAL and PSP. Now, luckily for us, there's no applied external force here. So solution is shorter. Okay. Any questions for number 3? Please answer in the chat. Okay. So I'm gonna end the lecture part there. I'm gonna continue answering on next week, Tuesday. Okay, so a few announcements. On Saturday, you have your quiz number 2. Coverage is strain up to indeterminate members. So thermal stress is not included yet. Okay. Now, on Saturday as well, I won't be able to meet with you guys. So that means we don't have Zoom meeting. However, our schedule for exam is the same, 3 o'clock to 4:30. Okay, so you still have to answer it within that time. But again, there's no Zoom meeting. So you have to upload or answer the exam by 4:30 and upload your solutions by the end of the day, or else you'll receive the deduction penalty. Okay? And then I've already finalized your Module 1 grade. We'll see it in your grade center. For those who got an IP or an I, please answer the IP exam. I've explained that last meeting. You have until the end of the term to answer that, and you'll see your score real time for MG1 for IP students. Okay? Any questions, clarifications, concerns? Okay, so If you've noticed you weren't able to do your assignment number one because we had holiday on the first week. So what I'm gonna do is your score for seat work number one will be the same as your score for homework. Seat work number two will be the same as your assignment number two. Okay, so same score. Yun lang. Okay, no more concerns. Again, quiz on Saturday. No Zoom meeting, but please answer within the schedule. Right? Okay, I'll see you on Tuesday. Since you don't have any more questions, you may go. Goodbye, class.